Good morning guys, welcome to today's worked exam answer video. Today I'm having a look at an AQA question whereby we've got this synthetic pathway, and the questions that follow are going to kind of break this down and think about each of the different reactions going on and conditions and writing some equations and naming things, and a very kind of standard AQA type of organic synthesis question. And then it also goes on to talk about like a condensation polymer, so the formation of nylon 4,6, and that links in because we're using this from one of the reactions, and I thought that was a really nice extra thing for me to cover within this video. So yeah, what I will try and do is mention as we're going through what is relevant to OCR students as well. Sorry, my cat's decided to join in and I had shut the blinds because it was a bit bright. Apologies. So yeah, we'll tackle each bit and I'll try and tell you which bits, if you're an OCR student, you need to be able to do. It's an AQA question, so AQA students, you need to be able to do all of this. Okay, so we are starting with acrylonitrile and we are synthesizing butane 1,4-diamine. And we can see that we're doing that via 3 different reactions. They've given us the reagent in reaction 1, we've got isomer W, and then we don't know anything about the others. So the first thing we've got to do is name isomer W. So whenever we have the CN involved, aka making it a nitrile, that carbon will always have to be carbon 1, and it should be obviously therefore included in the name of our kind of nitrile ending as a part of our longest chain. So that's going to be carbon 1, that's going to be carbon 2, that's going to be carbon 3. So that will then give me 3 bromo propane nitrile. Okay, 3 bromo. And it is really important when you're naming a nitrile that you put the E on the end of whatever alkane chain you have. So it was 3 carbons here, so propane. If it was 4 carbons long, you'd go with butane nitrile. They will be really picky about that E. So make sure you get that in there. And that would be the name of isomer W. Now it says reaction 1 produces a mixture of W and 2 other isomers. So we've got to figure out what those isomers are and then explain by considering the mechanism why all 3 isomers are formed. 6 marks. So there's potentially quite a lot going on here. Now, when I've done this question with students before, they've been quite happy identifying one of the other isomers but not the second one, and the first one that they're happier identifying comes from the fact we have this asymmetric starting material, and because we're using a polar electrophile, HBr, where the positive charge goes and where the Br goes once we get to the carbocation in the second stage is going to give us different products. And we're going to get them in different quantities because the carbocations themselves will have differing stabilities. So what we maybe want to start thinking about first is with isomer W, like which carbocation did that form from, so that we can then think about what the alternative is. So in order to put the Br on that end one, that had to be where the positive charge was. And so therefore when we opened up this double bond in the formation of W, we popped the hydrogen on this carbon, left that as the carbocation, and that's where the Br minus then attacked to give us 3 bromo propane nitrile. The alternative carbocation would therefore be to have the hydrogen going on to carbon number 1, the positive charge being on carbon number 2, and then having the CN there, and then that would form one of the other isomers, because the bromine is going to be on a different carbon. And so because we've moved the position of the bromine, that would be position isomerism, type of structural isomerism. And it hasn't said to identify what type of isomers we have, but that would be a position isomer of isomer W. And if we were to name that, we would see that it is definitely different, because carbon 1, carbon 2, that's where the bromine is, so 2-bromopropane nitrile is what we've made there. And those two carbocations will both form. This one is less stable, so we wouldn't get as much of W as we would as this structure here in blue, but we would get both. This would be our minor product, this would be our major product. But that's only one of the isomers, and it's very easy to kind of get stuck on this idea of it has to be connected to the mechanism of, in terms of like where your carbocations or where the positive charges on those carbons are going. That's not the case. And before I move on, in terms of answering this with 6 marks, we obviously wouldn't just be able to kind of write that, considering the mechanism why all 3 isomers are formed. So 2 potential carbocations can form in step 1 of the electrophilic addition mechanism, or adding across the double bond. The HBr is our electrophile. Now it might be a good idea, because it says explain by considering the mechanism, what that's going to look like. So HBr, and then from the double bond to the H, because that's partially positive, then from the bond to the Br, that's delta negative. That then gives us one of those 2 carbocations, the purple one or the blue one. And then from there, the Br minus ion can attack the positive charge on carbon 1 or carbon 2 to give isomer W and its position isomer. Which is this one here, which I suppose we could identify by name, 2-bromopropane nitrile. Now, there are many different types of isomerism, and what I've always suggested to students who have maybe struggled on this question is when they've got to this point to think, right, well, what other types of isomerism do I have? So under the umbrella of structural, we've got position, chain, and functional group. I can't see a viable way of us making a functional group isomer here or a chain isomer. We've only got 3 carbons in total, so we can't really rearrange them anyhow else. But there's also stereoisomerism to consider. So we've got E and Z isomerism, but that's only kind of valid when we have that carbon-carbon double bond and the restricted rotation. So that means that we're left with optical isomerism. Now, looking at isomer W, first and foremost, none of those 3 carbons are chiral. Carbon 1's bonded to the nitrogen 3 times, definitely not chiral. Carbon number 2 is bonded to 2 H's, so not chiral. Carbon 3 is bonded to 2 H's, so not chiral. So the idea is a chiral carbon will be bonded to 4 different atoms or groups. So that can't have optical isomers. What about 2-bromopentane nitrile? Aha! Carbon 1 is still a no, but carbon 2 is now a yes because it's bonded to 4 different atoms or groups. So this is where we're now going to draw optical isomers. So the non-superimposable 3D mirror images. So I'm going to write 2-bromopropane nitrile can exist as optical isomers or enantiomers. And because it says draw the structures of the other two, technically we've kind of answered that by drawing it in 2 dimensions, but I would argue it's going to be a better answer once we get it into 3 dimensions. So 2 bonds in the plane of the paper, this one, the wedge coming out towards us, dashes going back into the paper, and then mirror image of that, so hydrogen still at the top, CN going back into the paper, the wedge coming out towards us with the Br, and then the CH3 in the plane of the bond, in the plane of the paper. And so these are non-superimposable mirror images. So that's us having drawn our structures. Now I guess in terms of thinking about why we get these 2 optical isomers, yes, we have a chiral carbon, but we might also want to be relating it back to the mechanism itself. Now, this as an alkene, the starting material, the acrylonitrile, that around each carbon you will have a trigonal planar shape, so that will be completely flat. And when we then open it up, whichever carbon we put the hydrogen on, that will then be tetrahedral, but the other one still only has sort of 3 bonding pairs. Now, a bit like when we talk about nucleophilic addition, with the idea that because the C double bond O is flat, your nucleophile can attack the delta positive carbon from above or below with equal likelihood. It's exactly the same idea going on here. So it's not a nucleophile as such, the Br minus ion can attack the positive carbon atom of the carbocation from above or below with equal likelihood, which will give us a racemic mixture of these 2 enantiomers, which is just your 50-50 mix. And I don't think many students will have thought of optical isomerism here. So if it says isomers, generally try and remember all the different types and just work through and see which ones are possible and which ones are not. So we made a position isomer, and then that position isomer existed as optical isomers. Hopefully that makes sense. And then, as I said, really common for this kind of question, we're then moving on to think about reaction 2. So we've got to identify the reagent that is warmed with isomer W in reaction 2, and then state the other reaction condition needed. So when you've got the synthetic steps written out like this, I would always recommend kind of comparing, well, what did I have before and what do I have after the reaction has taken place. So we've gone from a bromine to another CN group being on there, so we've used the CN minus nucleophile, but of course we wouldn't want to write that as our reagent because the nucleophiles don't exist on their own. So you can either have sodium cyanide or potassium cyanide, and then the other reaction condition is that that would be dissolved in ethanol. And in terms of your mechanism, we've substituted, and the CN minus has acted as a nucleophile, so nucleophilic substitution. And I know that it's going to act as a nucleophile because it has a delta positive carbon that it can attack. And why is that carbon delta positive? Because bromine is more electronegative and thus will be delta negative. Okay. So far, OCR students, you would need to be able to do everything that we've just talked about so far, including what's coming next as well. So actually you might need to do everything in this question, which is, yeah, good. State the reagent and reaction conditions needed for reaction 3, give an equation. So again, it's looking at what's changed. So we had 4 carbons here, but only 2 of them had hydrogens on, and now all 4 of the carbons have hydrogens on, and the nitrogens now have hydrogens on. So we have gained quite a lot of hydrogen. So we're going to be doing a reduction reaction. There are 2 ways we can do this. The one I would personally opt for would be hydrogen gas in the presence of a nickel catalyst. Why? Just because it's easier to remember. The alternative would be LiAlH4, and that would need to be in dry ether, which maybe it's more memorable because it's a bit out there, but either or. In terms of the equation, it will depend on which reagent you've chosen as to how you will portray the hydrogen in your equation. So we've got NCCH2 CH2 CN. If we're opting for hydrogen and nickel, we can just write it as plus H2 and then H2N CH2 4 NH2. Now we're obviously going to need more than one H2. We're going to need 2 hydrogens on there, 2 on there, so that's 4, 2 on there, 6, 2 on there, 8. So I'm going to need 8 hydrogens, so I'm going to need 4 H2s. The difference would be if you were to do the LiAlH4 in dry ether, you would write that as like your reducing agent with square brackets and a H, and then you'd want 8 of those. So that would be if you were using LiAlH4, fusing hydrogen and nickel, top equation there. Okay? And that's kind of what we need to do with that little synthetic route. And there are loads of these in the AQA questions and in the OCR questions, and it is going to be a case of practicing, blurting out all your mechanisms, all your sort of reaction types, all your reagents, all your conditions over the next few days, unfortunately. But if you can do that and you're also happy with kind of recognising what's changed, and we understand what we mean by nucleophile and an electrophile and what we mean by addition and elimination and substitution, then you should hopefully, if you're giving something like this, be able to piece bits of it together. Conditions would be the one you probably couldn't do that with. Same with reagents, although you could maybe have a bit of a go in some cases, like something containing CN for reaction 2, but that would be quite hard. Okay. And then it says an incomplete equation for the formation of nylon 4,6 from 5 molecules of butane 1,4-diamine and 5 molecules of hexane dioic acid is shown. And we have to deduce the value for X, which is coming after the square brackets there, and then the value of Y, which is the balancing number in front of the water. So first thing, the reason why it's called nylon 4,6 is because one of the monomers has 4 carbons, which is the butane 1,4-diamine, and the other monomer has 6 carbons, which is the hexane dioic acid. So there's nylon 4,6, there's nylon 6,6, there's nylon 6,10, and that's what those numbers are referring to. In terms of how we go about forming this condensation polymer, and it is a kind of condensation polymer because we're going to be taking water molecules out, this is also an amide linkage. So this would be an example of a polyamide. Which is a type of condensation polymer, and I know that because of this repeating unit, this linkage, which would then be repeated in sort of every repeating unit. And when we join the monomers together, we're going to lose one of the hydrogens off of the NH2s from the butane 1,4-diamine. We're going to lose the OHs from the carboxylic acids on the hexane dioic acid. And then the C double bond O bonds to the N with the H, bingo, there's our amide linkage. Now, if we've got 5 of each of these, we're going to join the bits together in the middle 5 times. So x is definitely going to be 5, and the number that comes outside of your brackets is always going to be the same as the number of monomers that you have. Now, the reason why we're going to assign a specific number here rather than n is what we would use for any number. So we'd have n lots of each monomer, we'd have the repeating unit n times, and then we'd normally say we'd have 2n lots of water. However, we haven't got n, we have a very definitive number. We have 5 of each monomer. So first and foremost, that means that the value of x is going to be 5. Secondly, it means that because we're not thinking about like an infinitely long polymer chain, instead of just having the trailing bonds coming outside of the brackets, they've shown that obviously on this very left side of the chain, you will have to keep one of your diamine monomers with 2 hydrogens on it. So that would be the end of your chain on this side. And then we'd have this bit in the brackets 5 times. And then on the last hexane dioic acid molecule, you wouldn't take the OH off because again, it's not an infinite chain. It's kind of 5 repeating units long. So that's why the OH is then drawn outside of the brackets there. And that is going to have an effect on the number of water molecules formed. So every time these join together, we make 2 waters. So we've joined them together 5 times, but we haven't formed a molecule of water from these atoms here because they're forming the ends of our discretely lengthed chain. So therefore y would normally be sort of 2n, where x was n, but because we've used a specific number and we have to keep the ends on each end of our very short polymer chain, we need to then take one away from the number of waters that we would make, because we would not be taking this OH and this H from one of each monomer. And so we're going to be 1 water molecule down, and that's why y is 9. And I think that's quite a sneaky question, to be honest. Key things I would want you to be aware of: it's a polyamide, which atoms are lost in order to form that amide linkage, drawing the repeating unit, recognising water is lost, that it's a condensation polymer, specifically a polyamide, and then other things, I guess, like there'll be hydrogen bonding between the chains because hydrogen bonded to a nitrogen. They could be hydrolyzed, they are biodegradable, whereas addition polymers are not. But in terms of this particular question, it's understanding the idea of like n, 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 2n, but because we've then changed that for a specific number, we don't take the endings off one of each of the monomers, so we end up with 1 fewer water molecule being made. And hopefully that kind of makes sense. A lot of you have requested some more synthesis videos and NMR, and I will absolutely be doing those for you over the weekend. I'll try to get up as many videos as I can for you guys. It was really lovely how many of you messaged me before the paper 1 asking questions, and please feel free to do that again. There will also be more videos further back on my page that are organic, or you can go on my YouTube page where it might be slightly easier to find them. But yeah, let me know if I can help in any way, and I'm sending you all my best wishes and hope that you're taking care of yourselves. Catch you soon, guys. Bye.